The next two topics are a little weird and maybe slightly outside the scope of the class, but they also lead to interesting conundrums and also things that could potentially show up on the AP. The first is gravitation near the Earth's surface. Okay, so why isn't the acceleration of gravity, as I drop my pen cap, why isn't the acceleration of gravity on the Earth exactly 9.8? Well, there's a couple of factors that are leading to that. First off, we know that the force of gravity should be big G mn over r squared. And as we discussed in the last video, we know that the acceleration of gravity needs to be big G m over r squared if we're trying to figure out the acceleration of gravity on the Earth. It's not exactly 9.8. If we go around to different parts of the Earth, we measure something slightly different than 9.8, okay? So why is this happening? Well, there's three main factors that are contributing to this. One, Earth's mass is not uniformly distributed. So the first factor is that Earth's mass is not uniformly distributed. What this means is that the Earth is not a uniform object. Think about when we were dealing with rotations. Then we had a long cylinder or we had a sphere, and we always said that the object was uniform. That's not the case with the Earth. We have different types of material deposits, we have the oceans, different things are affecting the fact that the Earth is not uniform. The Earth is also not a perfect sphere. Earth is not a perfect sphere. Okay? The Earth is actually slightly egg-shaped. It is not, in fact, a uniform sphere. So since it's not a perfect sphere, that also contributes to why we do not have 9.8 meters per second squared calculated at every point on the Earth. The third one is the one that we're actually interested in. Earth is rotating. This is where we can actually get into some fun physics right now. Okay? Earth is rotating. And the rotation of the Earth is one of the reasons why we do not feel a perfect 9.8 meters per second squared. Okay? Think about you standing on the surface of the Earth. You have two forces acting on you at any given time. You have the force of gravity from the Earth that is trying to pull you down. Okay? The force of gravity trying to pull you down. But then you have the surface of the Earth pushing up on you. Pushing up on you. So you have the force of gravity down, and you have the normal force from the surface of the Earth pushing you up. Now I ask you guys, what is the net force on you as you're standing on the surface of the Earth? Dramatic pause. Some of you might say 0, okay? And I understand why you say 0. Right now I'm standing in front of you, doesn't appear that I'm moving, but I'm rotating. And since I am rotating, that means that there is a net force on me, and that net force is the centripetal force. Excuse me. So I have a centripetal force that is pulling me down on the surface of the Earth. So I have a net force that is equal to the centripetal force. Okay? Because I'm rotating on the surface of the Earth, there is a centripetal force pulling me down. Okay? So let's add these two forces up and let's see what's going on here. Okay? So the normal force minus the gravity force is equal to minus Fc, okay? So I'm adding up the two forces on the object. The normal force is positive because it's up. The force of gravity is down because it's negative. The centripetal force is pointing down, so I put a minus sign on that, okay? Now, the normal force is what you are actually measuring when you step onto a scale. You are measuring how much the scale needs to push up on you to keep you at equilibrium, okay? So we're actually going to solve for the normal force here. So we bring the force of gravity over, and I have that the normal force is equal to the force of gravity minus Fc. The force of gravity minus Fc. Okay? This right here, we're going to replace with m times g. Okay? So the normal force is m times g. This seems a little confusing, and the notation isn't great, but bear with me here a little bit. This g is what we are actually measuring. This is what we're actually measuring by measuring your weight, okay? We're going to replace this Fg with ma little g. This is the acceleration of gravity that we calculated up here using big G m over r squared, okay? That should be fixed. That should be 9.8 meters per second squared. and then we subtract your mass times the centripetal acceleration. And that centripetal acceleration is actually going to be omega squared times r. So what I've done here is I've replaced the centripetal acceleration from previous chapters, v squared over r. I've replaced v with r omega, and now I have omega squared times r. The masses all cancel out, and I apologize if this is getting a little low, but the g that we calculate is equal to ag, the g that we find, is equal to the ag that we calculated up here, minus the omega squared times r term. Okay? So this omega squared r, this rotation of the Earth, is actually taking away some of the 9.8, and so we don't get exactly 9.8 meters per second squared. This is a little bit of a weird concept. I would recommend reading it in your book. It's a little weird. I probably won't test on it, but it is something to know. This next one is even weirder, okay? Which is when we are outside the surface of a planet and we want to measure the force of gravity acting on us, we go from the center of mass out to the object. But what happens if we are inside of the planet? So what happens if we are, there's planet Earth. What happens if we are inside the Earth right here? And so we've got the mass of the Earth right there, and we're orbiting around it. So this is Earth, and this is our little mass. How do we figure out the force of gravity if we're inside the Earth? What happens to us? Okay? Now, believe it or not, Newton actually talked about this with his shell theorem. His shell theorem is what actually makes this very easy to figure out, and this is kind of the beginning of the higher level calculus that we're going to use in electricity and magnetism. Okay? So bear with me here. I'm going to do a really weird argument right now. Okay? Let's take the Earth argument. Okay? I'm up here orbiting around, so I'm at this position right here. And I'm going to imagine two lines, one cutting through like this and one cutting through like this, okay? What this is doing is representing my vision. Again, I said this was going to be a little weird. Bear with me. Please stop the video and think about what I'm talking about if you get a little confused, okay? This represents my vision. Imagine I'm in the classroom right now, and you guys know this classroom. I'm very far toward the front of the classroom, okay? If I turn around and face the wall, my vision, what I can see, is a very small portion, okay? If I turn around, I see the whole back wall of the room, okay? This is me looking at the whole back wall. This is me looking up here at the front wall, okay? So I have a small amount of mass up here that I'm very close to. Down here, I have a very large amount of mass that I'm far away from, okay? And the question is, the far amount of mass is going to pull me this way in terms of gravity. This is going to pull me this way. So I have a far amount of mass trying to pull me toward the back wall, and then I have the small amount of mass that I'm really close to trying to pull me toward the front wall. Newton's shell theorem tells us that these two forces cancel each other out. They cancel each other out. So what you have, this scenario, this very complicated scenario, actually begins to look like this. So you are now orbiting some new mass. So you cut away all of this material that's around you, you cut it all away, and you now have a new center of mass that you're orbiting. So you kind of ignore a whole portion of the object. Now that seems really, really weird, okay? Usually in these problems, they have to tell you what the density of the object is, because you have to figure out how much of it to cut away. It's actually a density problem similar to what you guys have done in chemistry. But the important thing is, we went from the mass of the Earth here and us some distance away inside the Earth to now a new mass with us a distance away, a new distance away, because we've shaved off all of this region. This is Newton's shell theorem. It's probably one of the weirdest things that we do in physics in this class. I can almost guarantee they're not going to ask you a question on the AP about it. However, it is the beginning of electricity and magnetism, so I did want to take the time to go over it, and definitely ask me some questions on this during my virtual office hours.